Welcome back. Here I would like to discuss section 3.3, which is actually the formal definition of a Brownian motion. So in the previous lecture, we have seen a rough idea of how to get to Brownian motion. We have seen the discrete version of Brownian motion, the symmetric random walk, in sections 3.1 and 3.2. It actually constructs a process with the properties that we will be listing now. So I'll start with a set of definitions. And first we need a formal definition, and for that we need a probability space. So let omega fp be our probability space. Now a measurable function w, which runs from omega cross 0 infinity, because it is a function of omega and time runs from 0 to infinity. So it is a random variable in omega, and time runs from 0 to infinity. And it will be taking values in R. Now the following properties are satisfied for W to be called a Brownian motion. First of all, if you fix T, and you look at the process, so we have W with an open space here, comma T. T is fixed, and the random event is variable here, is changing here as the argument. And we typically write this as WT. Well, actually, this is a random variable. Yeah, we write WT, but it should be understood as a random variable. Second one, now if we fix omega in big omega, then the function W omega t, where t is the running variable, that is, and omega is fixed, that is continuous, a continuous function in t. Moreover, we start at 0, so W omega 0 is equal to 0. And this is to be understood as Brownian motion has continuous paths. Yeah, the third property is about increments, and increments being normally distributed. And we write it as follows. Suppose we have two time instances, s and t, s being less than t. Now the random variable wt minus ws, which is an increment of w from t to s, that is normally distributed with mean 0 and variance t minus s. So part of the formal definition of Brownian motion is normally distributed increments with mean 0 and variance t minus s. And the fourth property, that is about the independence of the increments, and we can write that as follows. So here's our fourth property. Suppose we have now 4 time instances, S1 being less than T1, being less than S2, being less than T2. Then the increment WT1 minus WS1 is independent of WT2 minus WS2. Yes, so this is the general notion of independence. So we have, in fact, when we're dealing with Brownian motion and we're combining 3 and 2, we are dealing with independent increments that are normally distributed with a mean 0 and a variance of s minus t. So we know we have a lot of information about the increments. But now we would like to say something not about the increments, but about the terms themselves. So what can we say about the W's themselves? Well, first of all, let me remind you that what was in property 1, to keep the notation simple, we typically drop the first argument, and we simply write Brownian motion as a function of t being non-negative. So see it as a continuous time stochastic process. Indeed, it is a random variable in omega. Now we want to say something about the W's themselves, right? So from elementary probability theory, one can show that for any time instant, 0 less than T1, less than T2, etc., up to less than Tm, then the random variables WT1 up to WTM, they are jointly normally distributed. And in the book, this is also written in detail. And then we have to go back to chapter 2, page 64, definition 2.2.11. And these random variables, they are jointly normally distributed and they have a joint density function. So F, depending on multiple variables, x1 up to xm, and we sometimes denote this as a vector x. So this can be a vector x. That is then written, so the joint normal density function, that is written as 1 over the square root of 2 pi to the m times the determinant of covariance matrix capital C times the exponential function of with as argument -1/2 x minus mu C inverse times x minus mu, where mu is the vector of means. So it has m values, m mean values. And in the case of standard of these w's, the vector of means is actually a 0, right? So these w's have as mean 0. And C here, C, capital C here and here, that is actually the covariance matrix. And the covariance matrix, we have defined the covariance 2 lectures earlier. And each element in the covariance matrix, Cij, that is actually the covariance between WTI and WTJ. And that is in this case with the W's that are jointly normally distributed with mean 0, that is then equal to the expected value of WTI, WTJ. Yeah, because normally we have these two individual expectations added to it, but these are 0 in this case. So that will drop. And from this matrix with these elements, we need the determinant and we need the inverse here. Let me give you a brief outline of why this is true, why one gets such a joint density. So the idea of the proof is the following. So the joint event I'm interested in, that is WT1 being x1 up to WTM being xm. And actually the information that is contained in this event is equivalent to the information that is contained in the following event. WT1 being x1, and then WT2 minus WT1 being x2 minus x1, etc. up to the last one, WTM minus WTM minus 1 equal to xm minus 1. So the first one here you can see as WT1 minus WT0, where WT0 is equal to 0. So the information in these two events is the same. However, this second set is better manageable for us because these are increments. And for these increments, we know a lot. So the advantage of this second expression is that we know the distribution and they are all independent. And from this, we get a joint density, which is actually a product of these densities. So because of the independence of these increments, we get the joint density function as the product of these densities. F, we write it like ft1x1, so being related to this event here, times, because of independence, times f with subscript t2 minus t1, and an argument x2 minus x1, up to ftm minus tm minus 1 with as argument xm minus 1. This is then the joint density of Wt1 up to Wtm. And these right-hand sides are normal densities, and they have mean 0, and they have variance Ti plus 1 minus Ti, right? Or Ti minus Ti minus 1. Yes? So let us explicitly calculate some of these things. Let us look at the covariance matrix, and we assume that I is less than J. So Ti is less than Tj. Then this covariance that we need to compute here, that is actually the covariance of Wti times Wtj. And let's look at this. Because they are not independent, right? The W's are not independent. Now, as I mentioned, it will only be the expected value of Wti times Wtj. And what we do here is, in order to manage this, we add and subtract within the expectation sign, we add and subtract W square Ti. Yeah, we add and subtract W square Ti. And then we rewrite this as follows. This is Wti, Wtj, what we just have here. Then this one is the subtracted value. And here we add it again. Yeah. So we do this trick more often. Yeah. So now we know that these are independent of each other. So we can we have the linearity of the expectation operator. So this is the expected value of Wti times the expectation of this increment times the expected value of W squared Ti. And actually this is the variance, right? You see here a variance appearing. The second moment, which is the variance because again, the expected value of the Wti is equal to 0. So in total, this first part is equal to 0. The second part is nothing but the variance. And we know the variance of Wti, that is Ti. Yeah. Remember that we have explicitly mentioned and chosen that Ti is less than Tj. So in fact, the result that we get, Ti is the minimum of Ti and Tj. So in general, the covariance matrix of WSWT will be given by the minimum of S and T, right? So now if we write down this covariance matrix, so the part that is still missing from this expression of the joint density function, if we write down this covariance matrix, then on the diagonal, we will have the variance, right? That's the variance. On the diagonal, we will have the variance. That is by definition. And then, as we mentioned, each of the individual elements is the minimum of Ti and Tj. So that means that if I is equal to 1, it's always Ti here. The first one will be T1, and then it will be T2 from there on, right? From the minimum there is always T2, etc. So this will remain T2, then we will have T3, T4, etc. And the last column here is then T1, T2, up to Tm. And by this, we have defined our covariance matrix, right? So it is all related to the minimum of Ti and Tj. That is in fact our covariance matrix. And with this, we have completely defined the joint density function that we need. Now, let's look at the joint moment generating function. Why do we do all this? Why do we do this with looking at the joint density function and now looking at the joint moment generating function? Well, the definition that we had on the first slide of this lecture, it is a bit difficult sometimes to work with, right? We know the independent increments, we know the normally distributed increments, but it is much easier to work with a joint density function, which we have now in closed form, and also it's easy to work with this, with the moment generating function of a random variable. And remember from one of the last lectures, remember that it is written as phi of u, and it is defined as the expectation of e to the power x times u, where x is the random variable in the scalar case. So for just a plain random variable. And that is good. So what I'm trying to do here is to give an equivalent characterization of Brownian motion next to the definition. How to prove that something is a Brownian motion. The original definition, of course, says continuous paths, start in zero, independent increments, normally distributed. Yeah, this notion of independent increments, normally distributed, can thus be replaced by the joint distribution. And we can also characterize the distribution by means of the moment generating function. Remember that I mentioned that in a previous lecture, and this is a very powerful tool. So let's look at the joint moment generating function. And we will use this function quite often in verification. Recall this and now note that for any s less than t, this increment wt minus ws is normally distributed with mean zero and variance t minus s. And therefore, the moment generating function for this function, which I denote here as a subscript, wt minus ws, with argument u, is nothing but e to the power 1/2 u squared times t minus s. As you may remember from that previous lecture where I have denoted the moment generating function for a normal random variable. And it is important to note that the moment generating function uniquely determines the distribution of a random variable. Now we can also define the moment generating function of an R vector. Yeah, so of a vector. In our case, if we take m instances in time, and we are interested in the increments or in the joint distribution of wt1 up to wtm, then we can also derive the moment generating function. So that is written here on this slide. Now we take any m instances in time, t1 less than t2, less than t3, etc., up to tm, and we would like to find an expression for the moment generating function from wt1 up to wtm. And by definition, this is given by the expected value of e to the power u1 wt1 plus u2 wt2 plus u3 wt3, etc., up to plus um wtm. And we would like to find an expression for this expectation. again, this is not such a handy form, and we look at the exponent here. We try to rewrite the exponent in such a way that we get independent variables, because again, for us, it's easier to deal with independent variables. And WT1 up to WTM, they are not independent. So therefore, let's investigate the exponent, and actually we apply the same trick as before. We add and subtract terms so that we end up with independent increments. So this error, of course, I will repair before I post my slides. So we want to look at an expression that only consists of independent increments. So how do we do that? We do that as follows. So again, we have here in the first line, we just have our expression, so the expression for the exponent, mind you, the expression for the exponent, WTM plus minus 1, WTM minus 1, plus etc., U1, WT1. And now again, we add and subtract TM minus 1. So we add and subtract TM minus 1. Yeah. And if we do that, then we see that we have, this is the part that we subtract, right? A minus sign and a WTM minus 1. And of course, we add that too. So we have this here added, WTM minus 1. So all we did by adding and subtracting WTM minus 1 is we made this first term consisting of an increment. It's now WTM minus WTM minus 1. The other parts don't change. This one is added, plus the one that was already there, minus 1, WTM minus 1. This one, mind you, is just already here. And the other parts don't change. So we go on with minus 2, WTM minus 2, etc., all the way down to U1, WT1. And now we repeat this trick. We would like to get rid of this term here. Yeah, we would like to get rid of this term here. So what do? We add and subtract plus minus 1 times WTM minus 2. So we add and we subtract plus minus 1 WTM minus 2. This is the best I wrote on the screen so far. So this one was already there. And by doing this, we have added this term. So now it is plus minus 1 times an increment. Then this one is also added. So it's also here. It is plus minus 1 plus the term that we already had, minus 2 times WTM minus 2. And this one was already there. It was here. And this term is now added. And the other parts don't change. So this one was still there. minus 3, WTM minus 3, etc. up to U1, WT1. And we repeat this process. So again, we add and subtract a term that makes this an independent increment. So we would add and subtract plus minus 1 plus minus 2 times WTM minus 3, etc., etc. Yeah. And in the end, what we will end up with is this expression. So the first one didn't change anymore. WTM minus WTM minus 1 plus plus minus 1 times this increment, and all the way down to plus minus 1 plus minus 2 plus etc., plus U3 plus U2 plus U1 times WT1, which can of course be seen as WT1 minus WT0, which is 0. Yeah. And now we have rewritten, so by this we have rewritten the exponent as a linear combination of independent random variables. And for those, we know a lot. So we can benefit from this notion that we know that these are independent random variables. So adding all the terms, and then what we end up with is that the joint moment generating function of WT1 up to WTM with as running variables U1, U2 up to UM. I'll make this an M in the slides. That is then the expected value of e to the power, and then this expression, this independent increment plus this expression with an independent increment, etc., until this expression with an independent increment. Now, when these are independent increments, we know that we can apply some tricks. For example, we can write this as a product of expectations. The expected value of e to the power, the first term, times dot or times the expected value of e to the power, the second term, etc., times these times the expected value of e to the power, the last expression. And we know those, right? All of these are normally distributed. We know the mean, we know the variance, and we know that this joint moment generating function is then in fact e to the power 1/2 squared tm minus 1 plus 1/2 times plus minus 1 squared times this expression plus etc. plus 1/2, and then all the terms added, plus minus 1 plus etc. plus U2 plus U1 squared times T1. So we have a closed form expression for the joint moment generating function for this Brownian motion. So since the joint moment generating function determines the distribution, yeah, we get the following equivalent formulation for Brownian motion, right? This is an equivalent formulation for Brownian motion, and we call it 1 because we will refer to it later on. So we give it a name. Yes? Sometimes we call it star, but remember that we know the joint moment generating function for this Brownian motion. So now we have a couple of equivalent formulations. So let omega fp be a probability space, and let wt t greater equal to 0 be a stochastic process such that W0 is equal to 0. And for each fixed little omega in big omega, Wt omega is continuous. So we are dealing with a random variable, a random process, a stochastic process with a random process, and it is continuous. Then, by definition, Wt greater equal to 0 is a Brownian motion. That is the same as saying, first of all, for all these times 0 less than t1, less than t2, etc., less than tm, then the increments wti plus 1 minus wti, they are all independent, normally distributed with a mean 0 and a variance ti plus 1 minus ti. That is the first equivalent expression. The second one is that for all time instances 0 less than t1, less than t2, etc., less than tm, then this vector wt1, wt2 up to wtm, so they are normally distributed, joint normally distributed, and they have mean 0, and they have a covariance matrix C that is defined as this, the minimum of Ti and Tj. So T1's over here, T1's over here, T2 over here, T2 over here, etc., all the way up to Tm. Yeah. Then the third one is the moment generating function of a Brownian motion is given by 1. So it is given by this expression over here. That is an equivalent definition of Brownian motion, in fact. Now, what we also like to define is the filtration for a Brownian motion. So we need to say something about the filtration. Let omega fp again be a probability space, and let wt, t greater or equal to 0, be a Brownian motion defined on omega. Now the collection of filtrations, calligraphed ft, t greater or equal to 0 of sigma algebras, that is a filtration for Brownian motion if the following properties hold. First of all, fs is contained in ft when s is less than t, for all s less than t. And that is equivalent to saying information accumulates. The further we get into time, the more we know about the process. Secondly, wt is ft measurable. That is also known as adaptivity. And it basically means wt, t larger or equal to 0, is adapted to the filtration. Third, when s is less than t, then wt minus ws is independent of fs. So there's an independence of future increments. In other words, so we have seen that also for the symmetric random walk, for example. In other words, the sigma algebra of wt minus ws and the filtration to time ts, they are independent. And as an example, ft, script ft, the sigma algebra of ws, where s is less or equal to t, that is usually called the natural filtration of the Brownian motion. It contains the sufficient information and nothing more. Therefore, the filtration is equal to the sigma algebra. Now we have the following proposition. We want to say something about the martingale condition and Brownian motion. And you see that, in fact, we follow essentially the same steps as we did for the symmetric random walk. And we also follow the same techniques to prove things in this, for this continuous process. Yeah. Let f t greater or equal to 0 be a filtration for the Brownian motion, wt, t greater or equal to 0. Then wt is a martingale with respect to the filtration, and we can prove that as we always do. Yeah. So first of all, it's measurable. So that is it is adapted to the filtration. So it is a measurable function. And for the rest, the proof essentially goes as that for the symmetric random walk. And that we did as follows. We want to look at this conditional expectation. We want to look at the expected value of Wt given the information, the filtration, up to time s. And we want that to be equal to Ws. Yeah, that is a property of the martingale. So the best estimate for the expected value of a process is the value of the process up to time Ts, right? If we know the process up to time Ts, then the best estimate is the value that we know. It is something like a definition of a fair process. All right, now we apply essentially the same trick that we did before. So the expected value of Wt given script fs, then we add and subtract Ws. So we make it an increment, the expected value of Wt minus Ws, and we add Ws. So minus and plus, essentially we do nothing, right? We add something and we subtract it again. We add it and we subtract it, given the information structure up to time Ts. Now, expectation operator is linear, so we can chop it into two pieces. It's the expectation of the increment Fs plus the expected value of Ws Fs. Well, this is measurable function, right? And we can say, take out what you know, and we know this, so we can take it out of the expectation operator. That is just Ws. And here we have the independence. This increment is independent of the structure of the filtration Fs. And therefore, this conditional expectation gets to be a normal expectation. It's just the expected value of Wt minus Ws. And we know the expected value of this increment is equal to 0. So in total, we have 0 plus Ws, and that is equal to Ws, which is exactly the value that we were looking for. So indeed, the proposition Wt is a martingale with respect to the filtration. The tricks we did are the tricks we often repeat. We add and subtract Ws. First part is independent of Fs. The second part is Fs measurable. All right, that's it for now. And next time I will start with the quadratic variation of this process. Thank you for your attention. See you.